thanks everyone. So my name is Min. I go by that, like the minimum function. So that's my standing joke for introduction. Um, so this talk is based on something that you may have read or heard references to. How many of you know who Daniel Kahneman is? Any one of you? Have you heard of a book title called Thinking Fast and Slow? Yeah, okay. He was the author of that book. So this is, a parallel talk that I gave 7, 8 years ago before Transformers really took off, about the parallels of thinking fast and slow in research. And I also give this talk to our beginning doctoral students because I think they need to know as well. And you're all talented people. You answered wrongly, but very impressively that Odyssey was a great summer program. It is. And so I hope you have taken that journey because I think most of you are new too already. Okay. All right. Okay. So I'm talking about this gentleman, Daniel Kahneman. He talks about in psychology, he was one of the founders of cognitive science. Okay. So he came up with this idea of pulling off the cognitive science literature before it was called cognitive science. And he said, basically, if you look at the literature, there's like two different systems about how people make decisions. All right. And without trying to give credit to particular authors, he just called them System 1 and System 2. Because if you start naming it after people, people get politicized. Okay. So System 1, as it says in the column there, right, it is sort of a fast thinking system. It's pretty much automatic. Like you don't have control over it. It's also sort of intuitive. It does things in parallel and it's associative. So this is a lot of what we do in reaction. Like I'm walking around the room, I'm not like physically thinking how to move my joints, okay? And I'm not physically thinking how to move my vocal cords to talk to you. I have a message that I want to pass to you. But all of those things are being made by my body, right? So I'm not actively doing those things. So they're fast, they're automatic, and they're intuitive. Okay, but if you look at system two, it's quite different, right? It's a different modality that we work in here. And these are things that are more akin to what we think of human traits, right? They're things that are very slow and deliberate, like when you decide where you're going to eat or decide whether to buy the latest gadget or things, right? We engage in what we call rational thinking. Of course, we all know we are not rational beings in any sense of the word, okay? But it is a slow process. It is something that is very deliberate, right? You can't like just decide without deciding to decide, right? And it is something that doesn't happen in parallel, right? Like I can walk, I can breathe, I can gesture, I can talk at the same time, but I can't think about what I'm going to eat and whether I'm going to buy the latest gadget all at the same time, right? So this is something different. And most importantly, we call this also logical mode of thinking, even though in a logical sense, like you've been taught, maybe been taught with any um, discrete math course, discrete logic, it's not like that. Okay, so I want to ask you a question. When you think about AI, for the most part, like camera systems, face detection, etc., which system do we really think it's more like? System one or system two? Okay, this is where I'm actually asking you, okay, not like lecturing. So you guys are research students, right? You like to ask questions. You're inquisitive, curious even. You dare to speak up in class. And it's okay to be wrong, right? So what do you guys think? More like system one or system two? System one, your name, sir? Tapan? Okay, Tapan says more like system one. Okay, and so I would argue he is correct, right? So when we think about a neural net that does face detection, okay, that does translation or other things, okay, these things are basically very good at doing things very quickly, right? They're not at the time okay, even today, very good at doing the slow, controlled analytic stuff that we now, over the last 2 years, come to associate with, foundation models or large language models, right? Okay. So if you look at that, that was all pioneered by certain people in the field. Andrew Ng was one, right? Who came up with the idea of using a neural net because of, I'm sure you've already heard, GPU data, etc. Okay, that preceded the culmination of algorithms, hardware, and data all pooling together to be able to get our current round of judgments through AI. Okay, so I'd like you to think about, if you know a bit about AI, you will also know this idea of a loss function. Who's heard of a loss function before? Okay, when we train an AI, right, we train it on data. Okay, and I think everyone here knows supervised learning. Have you heard of that term? Okay, supervised learning is I give you an X, some tuple that represents some data, right? And I give you a Y, which is an answer, like an MCQ answer. And I ask you a question, and I give you many sets of this, right? And then I ask you to learn a pattern from the X that maps to the Y. So it's basically learning a function, f of xy, right? And that's the function that I learn, right? I approximate that function. So that's supervised learning. Now, in the process of doing supervised learning, we need to get the weights, the model parameters, usually indicated by theta or something like that, to decide whether a certain answer is good or not. Okay, so if you answer a question and the answer is supposed to be 1, but you answer 0.98, probably that's a better answer than something like 0.7 or 0.2. Okay, I mean, just let's say you have to make a decision between 1 and 0. Okay, a loss function is measuring this, right? It's saying how bad is it, right? So you can say, oh, 0.98 is 0.02 away from 1, so that's not so bad. If you answered 0.2, that's 0.8 away, so that's worse, right? So that's a loss function. That's how we get the neural network and other systems to better approximate, because we want to just tune the parameters so that difference between the actual Y value, the ground truth, and the Y value that the system is guessing gets smaller. Right? So we call this a loss function. I like to joke in the machine learning class that I used to teach that, it's very fitting Singapore because we're kiasu, right? So it's always about regret or loss, right? So you want to minimize that. We don't really incentivize machine learnings by giving carrots. We always give them sticks, right? We punish the learner when it makes mistakes, but we don't give them carrots, okay? So I put this thing for you to think about. When we're doing research, okay, what is the loss function of research that pushes us in the direction of having more creative, more broad-ranging, diverse, and more catalytic research, okay? So I'm going to talk about another book, okay? This is a popular science book, very nice. I definitely recommend it to you. Okay, it's called Thank You for Being Late. It's by this guy called Thomas Friedman. He's a popular science writer. And he writes about three accelerations that happen, okay, are happening, okay? One is Moore's Law. I think everyone knows what Moore's Law is, doubling of compute, everything else, right? So, a lot of things don't follow Moore's law, like how fast cars goes have been developed over the century. The last couple of decades hasn't followed Moore's law. We're driving roughly at the same speed. If we were driving at Moore's law innovation, we could get to the moon and back in about 5 seconds. Okay, but that's not how cars have evolved. Okay, but that's how computing has evolved. Okay, globalization. Okay, you can argue that sort of trend is going away, right? But the idea of the supply chain being outsourced to many different places, and this further specialization and siloing, that will help encourage more compartmentalization, more specialization, okay? And Mother Nature itself, right? Like we have global climate change and things like this. So there are a lot of things that are interconnected and affecting each other. And he's saying these three accelerations that you see in all things are synergizing over each other, okay, and causing more and more rapid disruption. I mean, we see that every day. People are talking about jobs being lost to AI, and we have some vindication that that's actually happening. Okay, so the idea behind this is that things are happening very, very rapidly to the point where our systems, our human society, are not able to adapt very well. Okay, and he makes this analogy to the second half of the chessboard. Does anyone know the apocryphal story about how chess was developed? Who's heard of that? How many of you know the game of Western chess? One? Are you sure? Come on, guys. I know it's early, but come on, I'm awake. I'm trying to give the lecture to you. One, two, three, four, five, six, seven. Okay, most of us. Okay, so the game was supposedly invented by a peasant, okay? And then he sold it to a prince. Do you know this story? Okay, so I say it's apocryphal because nobody can confirm it, right? So the idea was, okay, how did this happen? Okay, the pauper hosted the king in I think a dinner or something. He came to his house, and the king said, I'm bored. Can you introduce something interesting to me?" And the pauper taught him the game of chess. And the king was very impressed. He said, "Oh, this is magnificent. I really like this game. Um, how much do you want to be rewarded for teaching me this game? Because I'd like to entertain other people with it." And the pauper said, "Well, I'm not asking for a lot. I'm a humble pauper, right? I would just ask a very small favor. I just need some rice to feed my family. Okay? Oh, sure, no problem. I can give you plenty of rice. I'm the king of the kingdom. No problem, right? How much do you want?" And the pauper said, "Very simple. You put one grain of rice on the chessboard. You see this 8 by 8 grid, right? Put one grain there. Okay? Put two grains in the next square. And then on the third square, just double what you had on the second square. That's four grains. And just do it for the whole chessboard. And I'll be very satisfied." Okay, the king, of course, not thinking through the law of exponents, readily agreed to that, and the rest is history. Okay, so the whole point of this is things look very linear at the beginning, but even then it doesn't seem like there's a rapid bit of change until you get to about 2 to the 32, which is the second half of the chessboard. Okay, things after that look crazy. Okay, and so that is what he's arguing, is that the acceleration is reaching to that state where all of these things, these accelerations are happening and creating a lot of societal chaos. Okay, and it means chaos for us as researchers as well. So when I was young, I played video games. I'm sure most of us have played video games. Okay, my son plays them to the extent that I want to like kill him for playing too much. Okay, but one of the games that they had is a simulation game. Okay, it was created by this now defunct software company called Microprose, and there's a technological invention called the Galactic Cybernet. And it's so I had to pull up the text for this and then insert it back because it was too low res to read very well. So you can see I sort of crimped the slide there. So nearly instantaneously galaxy-wide communication accelerates the exchange of information and ideas, greatly accelerating the research capabilities of scientists and spying power of agents. 100% more research than your previous level of research. So when you get this upgrade, like, you know, your research goes mad. Okay, and we have a system that's called that. We've actually invented this. This is called archive. Okay, who has heard of archive or read papers from there? Okay, yeah. So archive was invented. It was an outshoot of the libraries branch of Cornell. They still run it. Okay, they're always asking for money because it's a very high demand service. But basically, that means that we really now have a very easy way of exchanging scientific information. Okay. So this is the premise of this talk is about research fast, okay? Research fast means we accelerate research to the point where things get very much second half of the chessboard, okay? So this is a very old graphic. I mean, this again, this talk is about 10 years old. It needs to be updated. But it's, I mean, the basic thing still holds true, okay? Oftentimes when you go to Google Scholar, what they will tell you, and you can look everyone up in SOC, okay, is how many papers you've published and how many citations you've gotten. Now, citations, they take a while to bring to fruition. It's sort of like a crop that you have to tend and harvest, right? Because you write a paper and then people have to read your paper. They have to like your paper so much that they want to give you credit, okay? And you guys have to do that, right? You guys have to read research paper. You have to credit the statements that you write, right? And say, okay, X, Y, and Z said this, square bracket one or whatever citation notation you have to give, okay? And then Google Scholar, Semantic Scholar, all these like crawling bots out there, they gather that information and they add +1, like or favorite, right, to the scholar's profile. Okay, so that's the part all the way on the right? It says there, citations in other articles and policy documents, right? But if you want to get an idea of how fast or how useful citations is, you don't want to wait months. You don't want to wait years, okay? Some of our colleagues in the other department here, called Department of Information Systems and Analytics, they take 2 to 3 years to publish a single article. And that means, you hire somebody, you want to know whether they're productive or not, you have to wait 5 years, okay? So, in any other job, you couldn't wait 5 years to decide whether to keep somebody or not, right? But that's what you have to do if you use citations as a rule. Now, if you go further and further to the left, you can see that things get a little bit more fast, right? Because the x-axis is time, right? So x-axis here is when the research is published, and you can see it's sort of like a logarithmic scale, right? So the whole point is that now people are pushing further and further to the left of this chart, right? They're saying, I don't want to wait for citations to see whether something is interesting. I'll just go to X. I'll go to Blue Sky, or I'll go to, even YouTube, right? Because people make videos about their research too, right? And I'll see whether somebody's commenting on it. And if they comment good things, or even if they comment at all, because all press, no matter how bad it is still good press, okay, is attention and impact, and therefore arguably something good, okay? So like you can see on the left side, there's first tweets appear, but if you believe that we'll have a galactic cybernet and we can trade thoughts, maybe that'll be even faster, okay? So my question to you is, are we getting to the point where we're going too fast, all right? Is going fast a really good idea, okay? So the picture behind us is a picture of an assistant and a scientist. Do you see 2 people there? No, I don't. Okay, so something else is going on. Do you know which one is the scientist? Is it the person standing there? No, it's not. Okay, that is the assistant. Where's the scientist? Come on, you guys, wake up. Sir, your name? In the computer. Your name, sir? Vikram. So Vikram says in the computer, and he's right. This is an automated scientist. Okay? It's a biological automated scientist. It makes its own hypothesis. It makes its own reagents, and it needs the help from a human being to actually do the work. Okay? But it's formulating all of the scientific hypothesis and testing on its own. It's assembling the experiment, and it's asking the human to go refill the bottles of the reagents. Okay? So we have, in some ways, I would say, like Thomas Friedman said, okay, our own accelerations of research, okay? One of them is what I said, preprint, archive, right? And so I've written the words that I can't write myself, okay, kiasu, okay? Meaning that because people like to archive and preprint research, now a lot of people are in a mad rush to publish before other people, right? You'll hear that from PhD students. Even some of you may be like, oh, I want to do this research, but I'm worried another team is going to put it out before me. So I'm going to plant my flag early. I'm going to preprint it, even though it's not peer reviewed, right? So peer review, I think is something that we do in science. It means that other scientists get to vet our work before we're allowed to tell it to everyone, okay? Because we think value through vindication from others is helpful. Okay, like they can tell us whether we're just not thinking very clearly. Okay, another thing that you see a lot is number two, right? Toolkits, right? How many of you have gone to GitHub to look up a research paper? Okay, Vikram, Miss, your name?
Lavinia.
Lavinia. So can you tell me about what paper you looked at? Do you remember?
Yeah, so it was actually, it was implementation, like what the where they ran the model and things like that. So it was on something known as fact card. So for the LoRa models, they actually ran this. They came up with this card, they call it fact card, where they were able to detect if the adapter was benign or backward.
Mm-hmm.
There they had a code implementation in the GitHub. So I went there to just look through that.
Great. So a brilliant example. So Lavinia said that she looked up a LoRa paper, so a low rank approximation paper that's supposed to squash a neural net into something smaller, like called an adapter, right? And so the people who wrote that paper likely also made their code implementation of what they wrote available open source on GitHub, right? And we all know GitHub, we love it. It's basically a photocopier for code, right? So basically you can just press a button called fork and then you get a copy of the code and then you can tinker with it yourself, right? So that's another acceleration because not only are our information about what findings we found available, but now our experimental code can also be available. Okay, now the third thing is shared tasks. Anyone know what a shared task is? Okay, yeah. So a shared task is a task established by the community as something useful that we want to synergize a lot of people to do. Okay, in information retrieval, which is like search engines, right? Search engines have this um, annual meeting. It's called the Text Retrieval Conference. Okay, and every year what they do is they get together and they say, all the search engine companies and search engine labs, we are going to have certain things that we want you to try to do with your search engines. Okay, and you guys are try to tune your search engines the best possible to get good results on this. Okay, so in the early times, that search engine competition helped people like Lycos, Yahoo, all these companies that are dead, Alta Vista, okay, and companies that still exist today like Baidu and Google, optimize their algorithms to speed up and give you better results for search. Okay, and we're seeing that all over again in something called retrieval augmented generation. Okay, so if you know about RAG or you've heard of it, a lot of these technologies that were already thought about many years ago are reappearing. Okay, so it's an exciting time for IR research. Okay, but the whole point is that shared tasks, again, funnel the community to think about certain things all together. And you can tell what this means. It means that there's less diversification in what people do. Okay, so all of these things, these free accelerations, all favor fast science because it's easy to replicate code. You just press a button. It's easy to read other people's idea. Just get the PDF. It's easy to do a task because somebody's already set up an evaluation framework, told you how to succeed. I tell you the evaluation metrics, okay? And all you do is, tinker with some code, submit it, and then we have a leaderboard, right? I mean, you're all familiar with leaderboards, right? Because in some of our classes, we have them too, right? A leaderboard for, I think, uh, uh, CS2109 has a leaderboard for certain tasks that they need to do for the Introduction to Machine Learning course. Okay, so, one other problem is that our scientific peer review, like I told you before, peer review means we don't publish things directly, right? We have to pass the barrier of what other people say is good research, okay? And so you usually submit an article for publication, then it gets reviewed by 3 different people. Generally in CS, we don't know who these people are. Some people like to guess and they think they can guess properly when in fact it's shown that probably they can't for many cases. But there are some problems with this, right? So reviewers also favor defensible positions, right? So I've put a joke up here. Here's a neat summary of the current state of interpretations of skull comparisons in biological Anthropology, male, female, white, black, rich, poor, gay, or straight. And these are all pretty much the same. Okay, I inserted my own one. Okay, reviewer two. Okay, like a Neanderthal. I mean, how are you to reject my paper? Right? I'm doing good research here. I'm trying to get science good. And you go blast the paper and say, I don't understand it, reject. I don't want to see this paper. Right? So, is this a good idea or not? Right? Because we want to maybe accelerate research, right? If you believe in research fast. So you will call your reviewer to a Neanderthal, right? And say, no, I don't want that. So in CS, for example, you probably understand that because we preprint a lot of stuff, it's not even peer reviewed, okay? But even in peer review, we don't use journals as much as conferences, okay? Conferences happen on a yearly cycle. The next one that's coming up that's very big, you may have heard, is Triple AI. It's coming to Singapore. I hope you guys will have a chance to attend. But just as of late, I think just earlier this week, they told us there are 29,000 submissions, of which 20,000 come from China, right? So that's a very big geographical shift in the center of gravity for AI research. Okay, so if you haven't seen a diagram of a loss function, don't worry, okay? Basically, what I am showing you is just a made-up function, a 3D function, okay? The x and y are some parameters, okay? And z is the value of what we want. So a higher value might be better, but in machine learning, we tend to minimize loss, so lower would be better, okay? So you can see, for example, if we set the x and y to something like this, where the x here would be 0 and the y would be like 0.05. That looks pretty good. It's close to this minimum here, right? Okay, so when we optimize parameters in a machine learning environment, that's what we do. We try to find the lowest place because we want the lowest loss, right? Okay, so when you think about a machine learning system, okay, with a configuration, with an X and Y coordinate, we have to set it appropriately. We do something called gradient descent, okay? One of many algorithms, right? And the idea is like we find the slope or gradient of where the function is sitting at, and we try to move to a lower spot. So like going down a mountain, right? So here you can say, oh, maybe I was over here and I want to go down the mountain. I want to go this way until I get to this bottom point, okay? Now, we can also think about this in a very loose, generalized sense about research, okay? Research, okay? So we're going to pretend that Winnie, myself, and all of you in this classroom are researchers, okay? All right? And we are all scattered in our parameter space, everywhere, okay, in this 2D space, because I can't think bigger than 2D, okay? And what I want to do is make sure we cover all of the interesting ideas well, okay? And what do you think is happening when we have all of those accelerations? I sort of gave it away because I inadvertently showed you the animation, right? Come on, guys. What do you think is happening when we have all of those accelerations? Archive, GitHub, share tasks.
Research faster.
We do research even faster. Thank you. Your name? Zahan. Okay, Zahan says, I will get even faster, right? So the animation basically shows that, right? What happens is right there on the left-hand side, right? Accelerations make the gradients steeper, okay? That means there's more reward for doing things faster, because if I preprint faster, I can fork the code faster than anyone else. Then I can make a research buck, right? I can get citations faster, right? You probably know trading algorithms really care. I mean, trading as in financial trading, they really care about the millisecond difference, right? If you're 2 milliseconds faster than somebody, you can make $1,000,000, because if you can execute faster, it makes a big difference, right? Because you come to the same conclusion as somebody else, but you monetized it before the last person, and this accumulates, all right? So you talk to the people at Bloomberg doing machine learning, they say, really, I favor simple algorithms that parallelize fast, okay? So what this means is that overload will favor the convenient. If you're a beginning researcher like yourself, why would I want to think about really difficult questions when I can get started right away by forking someone's code and reading their PDF, right? Because, well, the affordances are there. you know? So we all end up gravitating the same direction, okay? You can think about we are all points in space, okay? All of us have a vector of showing us a velocity, second order vector of acceleration, okay? So all of these particles that are in the space are now being accelerated because the gradients, the steepness of this landscape are higher. So we're all going to fall like pebbles or rainwater in similar paths, okay? We're going to gravitate to what's convenient to do, right? Okay? And my argument is that really what we want? Okay? We know from gradient descent, okay, that sometimes you get stuck in local optima, right? So for example, there's this little part here, okay? It's sort of nice and indented, okay? It's shallow, and when you reach that point, there's really no way down that's obvious to you. You can pretend you're in a valley and you can't see out of it. Everywhere around you, there's higher elevation, right? So you say, I'm doing a good job. This is the best I can do. If I go this way, I'm not going to get any better, right? Okay. So if we're all stuck in local optima like this one, then how are we going to do good research? Because all of us are thinking the same thoughts, doing the same thing, and we're not really looking at the very vast space which research actually is. Okay. So uh, I tell this to the graduate students. Okay. What do you do when your experiments fail? Okay. You can decide, crap, it didn't work out. My hypothesis was wrong. Okay, that would be nice. Most of our graduate students don't make hypotheses, they just do testing. Okay, but when they do hypothesis, maybe they find that their hypotheses are not validated. Okay, they can say, oh, you know what? I don't have enough data. Maybe I need more data sets or I need more label data. Let me go get people to annotate data. Okay, because I need more XY examples, and then maybe my classifier, my neural net, or my LLM will generalize, right? Or you can then retry the experiment, right? Maybe the current results are erroneous. You used the wrong hyperparameters or other things in your system. So just try again because, I mean, neural nets are stochastic. They're not deterministic, okay? Unless you set temperature to zero. Or you can do something that's really like what we do these days, which is go back to your archive feed. Oh, maybe there's another preprint that I missed. Maybe there's a new idea that some other team has come up with. Maybe I can apply that, okay? But rarely what people do, because it's hard to do, is to study the problem, okay? Because there's so many other push button things that you can do to make your research seem better, okay? But I'm going to argue to you that research fast is not the solution. Research fast gets us a convergence of ideas, great, but it doesn't get us catalytic ideas that open new fields, okay? So you may know about the light bulb, right? Who invented the light bulb? Edison. So your name? Jahal. Okay, Jahal, of course I know. He's a research student in my group. Uh, Edison invented the light bulb. Is that true, actually? Vikram? Okay. Actually, the light bulb was invented about six or seven different inventors in various places, and it's sort of known that many of these teams didn't talk to each other. It was just that the technologies made it possible to invent the light bulb around the same period. Okay, why do we think of Edison as the right person who invented the light bulb? Okay, I'm going to answer my own question, which is that because he was an entrepreneur, he was an innovator, not an inventor. Okay, he went and took the idea of a light bulb and went to try to find many different ways of getting the light bulb to work because the technology was there, but all of the components, the fabrication was not. Okay, famously, he went through something like, I don't know, through his assistants and his marketing and his research and development, something like over 1,000 different types of filaments that they use in the light bulb. And he settled with a type of bamboo filament, okay, that when applied to a current would light up but not combust, okay? And it was important, again, to enclose it in a glass vacuum, okay? But still, there was a lot of components and fiddling to work with, Okay, so the whole point here is that, it's really not a eureka moment, okay, because there is many times when we think about research, it's not a single idea that percolates and changes the world. It's the implementation, all of the tinkering that happens, okay, and all of those trials and errors are not facilitated when we have research really, really fast. Because again, there's a limited amount of things that you can try when things are already given to you in a structured way. Okay? Okay, so when we think about the slow process of research, there are lots of different things that research students go through. Okay, first, it's like, for example, as a Europe student, which some of you may be doing already, okay, signing up for a project. Oh, cool, I'm going to be doing this new thing with a professor. It's not been tried before, okay, and then discovering how that works. Okay, then you go through the tedious part of reading tons of papers, then collecting data, and you're like, oh, there's so much stuff. I have no idea what it means, okay? And then starting to collapse that, trying to get some idea of what all of that things mean with your PhD student or your prof, trying to refine things and to say, no, this isn't relevant. You might have thought it was, but it's not, etc. And then making sure you can do experiments, communicate that research, and finally publish it, okay? So that is a part of all of the research aspects that we actually do as researchers, okay? So I like to give this hourglass shape to how people think about it, okay? So when you do publishing and communication, there's a nexus point there. That's the culmination of one part of the process, but it's by far not the end of it, nor is it the beginning, right? It's just one point in that process that makes it easy for people to discover, okay? And when we do all of this fast science, we forget a lot of these steps in the process, okay? So when we read the literature, it's the same, right? We have to start from a very broad idea. We start from the title to see whether it's relevant. We look at the authors. Sometimes we know certain people in the field are related to the field that we're interested. We might read the abstract. We might even read the introduction. And over time, we might scan the related work, actually try to replicate the methods, do an evaluation, and check off the references, okay? And look at slide presentations, YouTube videos, blog posts, etc. about all of that, okay? So all of that is research, okay? So when we think about doing research in the other direction, right? So I'm deliberately slowing down my voice, right? Is to slow down our research, okay? That can help us do things in a way that combats that problem that I showed you before, okay? Which is that we want to flatten this gradient. This diagram that I showed you earlier, we want it to look more flat, right? So when we do that, what we can do is we can say, oh, actually, I can afford to do something hard because I'm not going to gravitate to the push button of forking a GitHub repository. I'm not going to just read papers that are in my field in this narrow part of archive on LoRa, because even though I care about LoRa, I know if I go the same direction as everything else, I am subject to groupthink. I'm not going to think any differently than myself, than other people in the field. And guess what? I am under-resourced compared to Google, outfought by MIT and Stanford people because they have larger research groups. So I have to play a different game. I cannot be nimble while trying to accept the same assumptions that all the other teams are doing. Okay? So what we mean by this is then we have to develop as researchers the ability to combat in our own minds, okay, the want to do research fast. Okay, research fast leads to research, no doubt about it, but it leads to a certain type of research, and arguably, it won't help us. Okay, if you look at scientific paradigms, okay, I don't know how many of you have heard of Thomas Kuhn. Okay, Thomas Kuhn was a philosopher. He studied the science of science. Okay, he wanted to know how people came up with certain scientific revolutions. Okay, for example, why did we go from a Copernican concept of the universe where everything was heliocentric? That means the planets, the moons, everything revolved around the sun. Okay, to the place where the sun was no longer the center of the universe. right? Even before that, was the Earth was the center of the universe. Everything revolves around the Earth, okay? So all of these things have changed over time. And that didn't happen because of research fast. It took some catalytic point to say, you know what? The data is not supporting those evidence, right? I think there's something else at work. But all the people who are doing research fast will tell you, no, you guys got it wrong. You're barking up the wrong tree. Okay? So that is a problem because if we have that problem, we won't be able to catalyze interesting research. Okay? Famously, you probably also know that Geoffrey Hinton was a case of this. Who's Geoffrey Hinton? Anyone know? Hinton is the guy who, sorry, go ahead. Your name? One of the pioneers of AI. That's right. So Geoffrey Hinton studied neural nets when it was so uncool. Everyone's like, Psh, you're studying neural nets. Get off my sleeves. I'm studying conditional random fields. I'm studying support vector machines. Okay, all of that. I'm sure everyone of us who are professors in the room remember those paradigm shifts. Okay, and he continued to do neural networks. Why? Because he wanted to. He didn't care what other people were thinking. And of course, we know right now he has the last laugh. Okay? But it's not to say support vector machines and conditional random fields are not applicable. Who knows? The people who are studying those now might be the ones that people are scraping off their dust off their shoulders. And maybe they'll have the last laugh later, right? So just because it's easy to make a neural network because NumPy and Pandas data frames are here, doesn't mean you have to do that. Okay, there is value in looking other places. Okay, so there are some other things that you can think of here. They're more for long-term research students, like developing the slow hunch, sticking with things that don't seem very popular, and the Swedish fika, which is a habit that they have in Sweden. If you have gone on NOC or you know anyone who's gone to NOC in Sweden, they'll tell you about the fika. This is like a coffee break that they take and they just gravitate. They go to a lounge and they talk about things. And for the most part, COVID sort of killed that. Okay, so it's very hard for us to actually get together in a place where there is no agenda because everyone is thinking, I need to be productive, right? So don't stop for coffee, don't stop for kopi or tea, right? Just go get your things done, okay? But actually, there's a lot of value in having something called a university, okay? That's why we're here. That's why you're here, okay? But outside of the structured classroom, there's a lot of value for being physically present on campus. Okay, so another thing that I want to end with, or close to the end, is this idea of inconvenience. Again, this is about research slow, okay? So these characters in Japanese correspond to the term fuben eki, okay? And so if you can read the Mandarin, you can get some idea of what it means. It means the benefits of inconvenience, okay? And it's probably best illustrated by a nuclear reactor, okay? In a nuclear reactor, it is very, very hard to change certain parameters of the nuclear reactor. You have to be very deliberate, okay? You can't use a web app and say, oh, switch this off, okay? It doesn't work that way. And it's by design. We make it hard for you to adjust the parameters in a nuclear reactor. Why? Because there are huge consequences if you change them wrong, right? So there is a sort of benefit of being inconvenient because you actually have to think very hard. I want to do this step. I will do it, but I need to deliberately think about how to do it. Okay? And that thought process, that rational system two thought process, engages us to think more broadly about things. When we do system one, we fork a repository or we read a PDF, we are not engaging our entire system one capacity to think broadly about things outside of what we can do. Okay? So, one of the key things that I've argued in this talk is that you need to look at the actual data. Okay? If you're doing AI research, for example, okay, many people will look at a loss function, okay, and they'll see, okay, loss curves are descending, so things are good. Okay? But that loss function is compiled of many, many different data samples. Many, many different data samples. Okay? So it's an aggregate measure. Okay, let's pretend we're looking at healthcare data, and your cohort of data points has more females than male, and the loss curve is going down. Okay, so it looks overall good for the group, right? But if you look at the data, maybe you find out the outcomes for women are really good. The outcomes for men, generally not good. Okay, then there's a cause for you to investigate that. But if you look at the loss curve overall, you would never see that. You would just see this treatment looks pretty good. Outcomes are better for the whole group. Okay, so I should do it, right? Okay, that happens a lot. All right, when we don't investigate the data enough to really understand the underlying problems. You can say, oh, well, I just let the neural network deal with that. Okay, guess what? You're replaceable, right? Because now you've delegated it to the AI to do the work for you. All right. So the key point on this is we have to ask the right types of questions, right? We don't ask the right types of questions about our data and question it. We are no better than somebody who just uses a loss curve and so aggregates all of that information and tries to optimize for that, okay? And we have to look at what's the adjacent possible, okay? What I mean by that is even though you're in a particular area, maybe you're in databases or you're in networks or you're in game development or software engineering. There are ideas out there from other people, even in your same area of computer science, that have useful things to tell you, but they're coded. They are coded in a way that you have to think to figure out how they're applicable to you. Okay? The algorithm, it was used for traveling salesmen. Okay? We all know the traveling salesman problem, right? Okay, but I don't see how it's applicable to large language models, or I don't see how it's applicable to packet routing, or I don't see how it's applicable to I don't know, uh, diagnosis of cardiacs. What is it? Uh, yeah, yeah. So all of these types of things, right? So the problem is they are many times applicable, but we have to use our imagination, use our unique experience to try to do the decoding of what these signals are for our algorithms. Okay. So one final part, okay, which is that um, things have been changing a lot over the last couple of years. All right. So technology, as you can see, has had a very large, rapid rate of change, right? Okay. I argued that through the chess story, right? Okay? But the rate of change that we can adapt as humans, we're not nearly as good at exponential change. Okay? So there is going to be a growing opportunity gap, and we see this already happening, right? Where technology is being defined faster than we can define correct ways of using it in society. Okay? That's a very big problem because we are hitting barriers in which what we can imagine is actually coming to fruition. Okay, and this means that it will happen very much for individuals who know technology well, like all of you. You guys are 99.9% of the curve ahead of most of society. Okay, so many of us have the opportunity to show the way. But of course, when we think about companies or government or the entire part of humanity, we have lower rates of technological change. Okay, this is why it's hard to change something as big as a school, or even worse, a university, or even worse, a nation. Okay, so you can tell this is what I'm talking about: research slow and research fast. Okay, so we need to actually ramp up more of the work we need on research slow. Okay, we're not doing that. Okay, as a research community, what we do with time saved by looking at archive, by looking at GitHub, is we spend more time on archive and GitHub, and we accelerate those gradients that I showed you. Okay, that I argue is not always a good thing because we are missing out on parts of that research manifold, that chart that I showed you, that 3D figure, okay? Because all our data points, all of our scientists are looking in the same place, okay? And so the only thing we're doing is just trying to chuck the flag faster than another research group, okay? So we should actually use the time that we are saving by having things like archive, by having things like GitHub, and saying, you know what, I actually do have time to go to Winnie's class and listen to a guest lecture. Okay, I actually have time to go to this other lecture in the Department of Chemistry because Min told me those types of things will actually help me come up with ideas, even though I have to really actually think hard about it. Okay, so that's the end of this talk. Okay, so a lot of times when we see junior researchers, they start an experiment and say, Min, it doesn't work. I have no idea. Okay, and when we keep on working with this, we will see things like if we try to do things a little bit slower, maybe we can close the loop, look at the problems, look at the other types of research more carefully, then might we be able to come up with something like, oh, I was able to fix the problem, but I don't know why still. Okay, and then further for that, maybe we can get to the point where we actually know what things are happening. And this is a real problem in scientific research because many times we publish works, we say this works, but we never explain why. And we try to just throw up our hands. Neural networks are black boxes. I can't explain it. Too many levels, too hard to interpret. So I'm not going to try because I have a page limit of 8 pages. Okay, so sorry. And you want me to write a journal article? Forget it. I have to publish or I'll perish. Okay, so that is the whole talk. So I hope you have some questions for me because it's more interesting to get questions, but it's already 10. Sorry.